Hi, welcome to tonight or today's video, depending on when you're watching this, on simultaneous inequalities and specifically solving them if they have one variable in them. So, to get things kicked off, first thing we need to consider is what are we even trying to do when we're solving simultaneous inequalities? And to answer that question, it's probably worth taking a trip back to the other time we came across the word simultaneous in maths, which was simultaneous equations. And when we were solving simultaneous equations, we were trying to find x and y values that satisfied, in other words, solved or worked, in both equations we were given. Now, for simultaneous inequalities, it's a very similar idea. We're trying to find x values that satisfy both inequalities. Now, quite how we go about that will differ a bit from how we approach simultaneous equations, and that's partly just due to the issue we had when we were trying to solve simultaneous equations. The main issue when trying to solve simultaneous equations was just that we had two different variables, and so most of the method is concerned with just trying to eliminate one of those two variables so that we're able to solve it. As in this case, we're trying to solve simultaneous inequalities with just one variable, x, in them. That issue isn't really there, and so therefore, naturally, the method does look a bit different. So, let's show you how to do the method. So, I've got an example here, and it says find the set of values of x for which x squared minus 9x plus 14 is less than 0, and x squared minus 7x plus 12 is greater or equal to 0. Now, straight away, you're seeing that word and well, the word "and" in maths has a very strong link to this symbol here, the what we call the intersection symbol, which is designed to show the overlap between two things, and so that should therefore give you a clue what exactly we're trying to do once again, even in just the way the question's worded. So, how are we going to go about that? Well, we can start just by solving these two quadratic inequalities individually. I, for the moment, just treat them like their own, like they are each their own separate question. Now, that won't be the final answer, but it'll help us find the final answer. So let's go ahead and do that now. So start off by solving them like an equation to find what we call the critical values. And if I solve that quadratic, for instance, I get the values x equals 2 and x equals 7. But then, because it's an inequality, I then have to decide how the inequality signs are going to go, and I draw a graph to help me. And just a reminder, one way of the graph helps you is because you're effectively drawing the graph of y equals the quadratic, and then y equals the other side of the inequality. So in other words, the quadratic inequality is boiling down to where are the y coordinates of the quadratic less than y equals 0. Y equals 0, of course, is the x-axis, so it's saying where is the graph below the x-axis. And so, therefore, that would be this region here, and that would therefore be the x values between 2 and 7. Not inclusive, just because of the type of inequality I had in the original inequality. And then we do the same thing for the other quadratic inequality. We can start by solving it to find critical values. Once again, this time it'll be x equals 3, x equals 4. And then we draw a graph again to help us decide how the inequalities are going to look. Very similar sort of quadratic, but of course different x-intercepts this time. And this time we're looking for where it's greater or equal to 0, so that would be above the x-axis. So that would be this region here and that region there. And if we're looking at the x values that are solving and talking about those regions, describing those regions, that would be to the left of 3, because x is dealing about left and right, to the left of 3, so that's x is less than or equal to 3. Again, that's due to the fact we had a greater or equal to inequality in the original question. And then to the right of 4, so that's numbers bigger than 4, but then therefore specifically looking at x is greater or equal to 4. Okay, so those are the individual solutions to our two quadratic inequalities. What we're going to do now, though, is work or think about what x values work in both inequalities. So to help that, we're going to draw a number line. And we're not going to go to the effort of writing a whole scale on this number line. We're just going to mark on, just like we do with graphs, just the important values we care about. So first of all, let's represent this inequality on our number line. So doing this, well, let's say 2 is somewhere over here, 7 is somewhere over here. Then if we represent this inequality in the same way that we represent inequalities on a number line at GCSE, we would write a little circle above 2 and 7, not colour it in because it's not including 2 and 7, and then it'd be a line connecting those 2 points. Okay, so that's the first inequality done. We're now going to be representing this inequality, or set of inequalities, set of values on our number line as well. So first of all, x is less than or equal to 3. If we say 3 is about here, then that would be represented by drawing a circle above 3, this time colouring it in because we are including 3, and then talking about all the values smaller than 3, so that's to the left of 3 on the number line. And then doing the same thing for x is greater or equal to 4. Let's say 4's here. And then once again, a little circle above 4, coloured in to say that we're including it. And then we're looking at all the values to the right of 4, bigger than 4 in other words. And that goes on forever in that direction. Okay, so now we can use this to help us find what values will solve the overall simultaneous inequalities. Reminder, what we're looking for is the set of values of x that work in both inequalities at the same time. The values of x that overlap are the set of solutions we had for both individual inequalities. So let's have a look at what our number line says. For a start, we've got all these values over here. Now these values are below 2, so values like 1 and so on and so forth, and those values do satisfy one of the inequalities. X is less than or equal to 3, for instance. But they don't satisfy the other set of values we got from the first inequality over here. And therefore, we're not interested in these values because we only want the set of values that work for this set of values and this set of values. So we move on, and the next region we could look at is between 2 and 3, and what we notice straight away is we have highlighted those set of values for both inequalities. We said they worked for this set of values over here and this set of values over here, and therefore they are values that we want because they work in both inequalities. So therefore, writing that down, that would be the values between 2 and 3, but including 3 just due to the fact we had a less than or equal to inequality here. Okay, and then continue on, between 3 and 4, we have the same problem that we had less than 2 in the fact that those values do solve one of the inequalities, but not both sets of values. And then moving on between 4 and 7, once again, we're in the good situation where it's satisfying both sets of inequalities. So therefore, we do want these values, and that would be the values between 4 and 7, including 4, though, again, due to the inequality signs that were in the original individual sets of values. And then finally, above 7, we're back to the situation where it only solves one inequality, and we're not interested, therefore. So, therefore, these are the final solutions. These are the sets of values that work in both inequalities, and therefore we have found our solution. We are done. Okay, I hope that was useful for you, and I'm sure I'll see you in a future video.